Hello folks, this is one of the video segments that I'm preparing for support to the textbook that I wrote on Finite Element Essentials in 3D Experience, release 2021x. Okay, so this is chapter 10, by the way. I'll get to that in a minute. All right, so here's a textbook. It's published by SDC Corporation, SDC Publishers, and there is 18 chapters. The current chapter is chapter 10, which is gasket compression using analytical rigid surface. So the problem that we're going to be doing is a rubber gasket, which is sandwiched between two rigid plates, and these plates are squishing or squeezing the rubber gasket. Now, because we are assuming that the length of this uh, piece is very big, very long, in a sense, things don't change in the length direction, and that's stresses don't the strains don't change in the length direction. They're zero in the length direction. And this is what is called a plane strain problem in your stress analysis course. So what we need to do, what we can do, is we can take a sector of this. First of all, notice that because of the symmetry, all you need to do is to model uh, one fourth, one fourth of this circle, okay? And then because it's very long in the length direction, it's a plane strain condition. All we have to do is to take a, a, a little sliver of this out, and the length of it actually doesn't matter. Plane strain condition usually assumes that it's 1 unit long, but that's totally irrelevant. And we're not going to be doing it as a plane strain problem because in 3D experience, uh, the, the finite element solver, which is really abacus, uh, uh, does not have the two-dimensional model elements, okay? So we're going to be modeling something like that, where these front face, back face, bottom, and left, they're all planes of symmetry. In other words, the rollers. And the top, not going to model it as uh, with elements, either solid or shell. We're going to be using rigid surface, analytical rigid surface that's available. So this is the way I'm going to be modeling the problem. We're going to have two parts. One is basically the gasket, a quarter of the gasket, and the other one is just a plane, which is going to represent our analytical rigid surface. The dimensions are given here, and what we're doing is we're taking this plate and pushing it down by 100 millimeter. Now, the material that the gasket is made of is nonlinear, and we're going to model it with a Mooney-Rivlin hyperelastic um, model, which basically, well, the strain energy is given something like that. You don't have to worry about these things. All you need to know is what these values C10 and C01 are, which either you look it up or you do testing and extrapolate or extract this information. In real life, what we do is a series of uniaxial and perhaps torsion and shear tests, and that information you give it to some magic package, and it's going to extract for you C10 and C01. Okay, so let's do that. Let me put my dimensions here so I can see it. First thing, I'm going to log into my account. So, okay. All right. And now I'm going to log into, or on the top left corner, I'm going to use the compass to make my assembly, get into my assembly design workbench. So first thing that we're going to do is to create an assembly, and then in it, we're going to put those two parts. Just bear with me a second because this is all on the cloud, and it's now hooking up to some server in I think Europe. Okay. All right, so it's going to come up. Now, while this is booting up, the, the, the native solver, the finite element solver in 3D Experience is the Abacus program, okay? But you don't have to know Abacus. Basically, you start from scratch. That's what we're doing here. Okay, so there is my assembly. Let me rename this thing to make it gasket assembly. Gasket assembly. Okay, and I'm going to put my first part in it. So insert, 3D part, and this one I'm going to rename it. I'm going to call it the gasket. Gasket. Okay, and the instance, I'm also going to call it gasket. Okay, and we can insert the other one, but let's just insert the other one. So right click, insert, or we can do it after we make this part. And I'm going to call this the plate, rigid plate. How about that? Properties, rigid plate. Rigid plate. And the instance, the part, so reference, rigid plate. Okay, now we can go and make our rigid, well, the gasket. We're going to make the gasket. Double click on this 3D shape. Double click on it. You're going to be thrown into the part design workbench basically. So on a convenient plane, on that vertical plane, I will sketch the quarter of the circle. So let's see what's the best way of doing it. You come down here, use arc. Okay, and dimension this thing. I think the radius of that circle is 200 millimeters. My units are already in millimeters. Okay, and then we draw the line to close this. So I'm going to use the polyline. You go from here to here, and then I go all the way to the top. And this is it. Exit, and then we pad it. Now this is under the Essentials tab. Okay, Essentials tab. Oh yeah. Right now I'm not in the part design. I'm in wireframe. I'm in generative shape design. So let me switch to part design. Because I want to make a solid object, and I happen to be in the generative shape design, which is for surfaces. There's your pad, 50 millimeters. You say okay. All right, and this is it. So now we're gonna go. Why don't we save this thing here first? Then we're gonna go to the rigid plate. Double click on the 3D shape here. And rigid plate is really just, it's not a solid part, it's just a surface basically, okay? So on a convenient plate, on that same convenient plate YZ, I'm going to be sketching, I'm going to be sketching a line, horizontal line. Let's dimension this. Although the length of this line is not important, but just so that I can keep track of what I'm doing here, I'm going to make this thing 400. Is that right? 400 millimeters. And by the way, notice that this is not horizontal, so I can select it and right click. Can I make it horizontal? Yes, horizontal. That's one way of doing it. Okay. Now, this thing is supposed to be touching that, so there are different ways of doing it. For example, I can dimension between this point and that line. and make that 200, or I can create some kind of constraints there to do that for me. I think that's pretty much it. Oh, exit. Now, while I'm here, let me also make a point, which is that point on the top, which is called the reference point. So the height, the coordinates, with coordinates, and the x and y are 0, and the height is 300. If you look at my slides, you can see that millimeter, right? There we are. There's my point. Okay. Now, since the rigid plate is going to be basically a surface, so I'm going to have to extrude this thing. Why don't I go to generative shape design, where I was originally, remember I had to leave it, and then use the extrude this, and by a length of 50, I believe, 50 millimeters. Good. So that's pretty much it. We have done our model. So what I'm going to do is, first of all, let me go all the way to the top. This is at the assembly level. You can see it says assembly design here. Why don't we save this? Okay, now we can create our material. Okay, so first thing I'm going to do is, although it may be possible to, let me see, can we apply material? Can we create the material at the assembly level? No, the best thing to do is to go to part, gasket, go back to that part. Okay, notice that if you are we there? Oh, second line. Now we're in part design. You can see that. Actually, this is generative shape design. So let me actually go to part. And if you select the tools, you see that right there you can create material and apply it. So why don't we create a material? Create material. Let's give it a name. So also in my gasket, rigid plate. Okay, so we say all right, and all this does is basically creates a shell. Okay, it creates a shell in my database. It's somewhere here. I've got so many of them, so maybe I can sort this out in the by date, by modification date, descending. I'll call that my gasket rigid plate, right? Okay, so that should be the first one in the list, right there. My gasket rigid plate. Okay, and there's two ways to do this thing. One is, if you want, you can double click on it. Actually, let me do it a different way. Let me put the cursor there, right click and say apply. Okay, apply. And I'm going to make this thing smaller or close it. And I'm going to apply it to my gasket and then say OK, or check the green thing. Now, notice that it did create a shell for me. It doesn't have the data here, but I can input the data right now. See that? Double click on it. One more time. Okay, good. So it is a structural problem. Abacus multiphysics. It's mechanical. And it is elastic, but it is hyperelastic right there. Okay, and if you check this hyperelastic box, it will say, okay, what kind of model would you like to use? Well, in here there is a Mooney-Rivlin material. Pull it down, Mooney-Rivlin material, and you put your C1 and C2 directly in that box. Okay, so let me see now. C1 and C2. Let's see what they were. So C10 was 0.293 megapascal, 0.293. So 0.293 You can type MPA, or you can multiply by 10 to the 6. Let me type MPA here. Okay, didn't like it the way I typed it. So let's do it like this. 0.293 e to the 6, and the unit is, of course, the default Newton per meter squared. There we are. I think that's what it was, right? Yep. Yep. And the other one is 177 times 10 to the 6, which is 177 and 3 zeros. So this one is 177 and 3 zeros. That is the right unit. Okay, now we don't have to worry about this last one because we are assuming this material is incompressible. Moon-Rivlin is an incompressible material. Otherwise, compressibility can be brought into the problem by getting the right D1, but we're not going to do that. Okay, so this is it. Say okay. Notice that this material has been created here, the data that we want, that's all you need. Okay, so what is the next thing? Right, make sure you are at the assembly level, Why don't I save everything? And now you're going to go to the compass here and go to uh, uh, structural model creation right there. Okay. Use the default here. Don't change anything. Okay. And notice that what it did, it created a mesh automatically for you, which is that size right there, and the appropriate solid section property. It didn't mesh this because this is going to be done eventually with rigid analytical surface. Okay, good. So that takes care of this. Now, uh, right, that's pretty much it. The other thing I want to do is to create what is called an abstraction. So this surface is going to be made using this abstraction thingy. Notice that the abstraction tab is selected here, and in there I have different options. One of them is analytical rigid surface. You click on it. Okay, so it says the surface definition. First of all, I want to tell you, oh, yeah, this is the surface right there. And the point, the point, the point, I'm going to use this. So this is the reference point. It's called the reference point there. I select a reference point. There are other ways of doing it. You don't have to do it by a reference point. You can do it by mass center of, this plate and things like that, but don't. Now, keep an eye on this flip direction, okay? You will see that at some point you have to come and make some changes here. I'm going to take you down the path that will fail when I simulate it. And then when we look at it, we know what we have done wrong. We're going to come back and fix it, okay? That's on purpose. All right, good. Notice that here, a rigid surface, analytical rigid surface has been created. Basically, it's that plate, okay? That's pretty much it. So now we're going to go to our scenario, right? Structural scenario creation. You go there. It is a structural problem that we're doing. You say, okay. As soon as you do that, you're going to get these red exclamation marks, which means that you don't have a case and you don't have a procedure. Okay, so first of all, if you select the setup right there, see that? Setup. You need to basically create your finite element model. You need to click on this guy, finite element model. You click on it, and we already have meshed this thing. You can see that it's right here. It's already done. And we select it, and we say, OK. As soon as you do that, this red exclamation mark becomes a green one. OK, very good. Now we're going to go to procedure. You select the procedure. The problem that we are doing is a static step. Use the default values. Of course, if things don't converge, you have to come back, fool around with these, and we're not going to do that. And make sure that the nonlinearity, geometric nonlinearity is checked. This is under advanced. It is checked by default. I mean, a problem like that is definitely nonlinear. It's like it's a rubber that you're squeezing it really hard, etc. So this is fine, just very good. Now we're going to apply our restraints. Restraints right there, and planar symmetry. Because of symmetry, remember we took one-fourth of the cylinder. This is a planar symmetry. Unfortunately, you have to do this thing 4 times. We cannot select it all in the same dialog box. Another one, that guy. Another one, that face. And finally, the back face. These are roller supports, and they come from planes of symmetry because of the gasket being symmetric and the fact that it's a long gasket, and therefore we're solving it as if there was no strain, no displacement along the length direction. Okay, now we would like to take this reference point and push it down. The first thing that we have to do is say that this reference point can only move in a z direction. So that's done with this fixed displacement. We select the reference point, and you immediately a coordinate system is created. If you want to describe displacement in a different direction, you can rotate it, but this is fine for me. This does not move in the direction x and y. It does move in the direction z because at the end I'm going to come and push it down, and right, and then rotations, it doesn't rotate, it just comes straight down. Okay, and then I'm going to say, okay, where is the load coming from? We're done with this restraint. We go to the load, and there is apply translations right there. Okay, selected the loads tab, apply translation. You select this same point, and we're going to say that moves in the z direction by minus 100. Actually, the way they have done the programming here is that your motion is always in the direction of local z, okay? So all I'm saying is that just be careful with how you interpret this thing, okay? And that's pretty much it. So we say okay. All right. The next thing we want to do is to create interaction. Interaction means that, okay, this plate does not pass through that surface. Okay, so you click on the interaction, and the type of interaction, there are many different types. In this particular case, we're going to use something that's called surface-based contact. Now, for the green or M, I'm going to select this shape, this plate. Okay, now I'm gonna have to go and fix it. You'll see why. You select this. This is wrong, but that's okay. For the slave, for the S, I'm gonna select this curved surface. Don't do anything else. You say okay. When we try to run this thing, it's gonna complain, and we're gonna have to come back and fix it. Okay. So let's see now. Here, right there. So we say simulate. Before I do that, it's a good idea always to save. Okay, good. So this is called the model and scenario check, and it's going to fail at this point. You're going to see why. Okay. It says model and scenario checks fail. All right, so let's go read it. It says error, wrong support definition. Close this, wrong support definition. And when you read it, it says for supports, for surface-based contact include both geometric and feature entities. The support must be of the same type. And if you read this thing carefully, it says that, all right, you selected that face. I don't want that. Go and select the analytical rigid surface from the tree. So we say, fine, you're going to fix it. So let's go ahead and double click on this analytical rigid surface. I'm sorry, not that. Let's go in the structure analysis. Structure analysis. Under interaction, this is where the problem was. Double click on surface face contact. Okay, and don't select this because let me get rid of this and remove all. Okay, so for the green one, select the analytical surface, rigid surface. Don't go and select that face. Analytical rigid surface. Notice that it actually puts it there. Last time it puts a face there. And for the S, I'm going to select that face, just like before. You say okay. All right. Save it. Let's go do the check again. Let's go do the check here. No problem. Didn't bomb out. This is called simulation check. Again, it gives you warning and error messages before you actually run it. And very frequently we ignore these things, but sometimes you have to go back and read it. Okay. In fact, if you look at this, you can figure out what possibly the problem is. But on purpose, I'm not going to look at my warnings. I'm going to, since it lets me go and run it, it's not going to give me an error. I'm just going to run it. See that? Completed, no errors. Okay, close that. And then we're going to simulate. Okay, it's going to run, but it's going to be wrong. And you're going to see why in a minute. Notice that my mesh is very coarse. I didn't even bother checking what kind of element it uses. It uses tetrahedral, and I'm pretty sure it's quadratic, but we're not assessing accuracy. Notice that it did run. No errors, it did run. So this is before it actually does any squeezing, before this thing moves down. If you go after it has been squeezed by 100 millimeter, it goes through it. And we wonder what the heck happened. So you come and look at the warnings here, and then it says there are 12 facets that are found to be facing in the wrong direction with respect to the master surface for the contact pair. So it has something to do with that master and slave surfaces. So we say close, and we don't need this thing. Let's go back here to our surface base contact right there. Double click on it. Okay, there's nothing wrong there, but if you go back to the analytical rigid surface, remember I said we're going to come back here. There's something called flip direction. When you have contacts, they have to write the program very carefully so that the contacting surface and contact surface have normals that are pointing towards each other. Most of the time, that's the way it is. So if this doesn't work, basically it means that the contact didn't work and this guy just went through it. So my approach is first to flip the direction and run it and see what happens. Uh, there must be a way that you can display the normals here, but I'm not going to be interested. All I did was to say flip direction, and I warned you about half an hour ago that we're going to come back here and flip it. Okay, let's go ahead back to the scenario and run it. So this puts you back into the scenario. I'm not going to bother checking the model, etc. I'm going to run it because I know it's going to work. So I purposely took you down a road that failed because of two issues, but we found out how to fix it. Okay, just give me a minute. It's coming, it's coming. Just a second. Now notice that it's going further. That's because this is actually a nonlinear problem. It's going to do it in increments, and within each increment, it has to do iteration so that the results converge. So it's a fairly laborious process. It's not just like a linear analysis that it just does it in one shot. Okay, we're going to be done. If your problem is big, too many elements, etc., this thing can take very long. We talk about sometimes maybe an hour. So, but these are simple problems. We're not going to be worried about it. So it looks like it did because it's extracting the results, and there we are. So let's close this thing, and there we are. So increment one was actually initial frame, no load applied. This was not moved, and then this means that out of the 100 millimeters that you had to push it down, it's 25 it's 25 millimeter down, okay? And then it gradually goes down. And the last one is after you squished it by 100 millimeters. This is the one meter stress distribution. You can show other things. For example, you can see the displacement. These are the displacements, okay? You can see that this pushing down 100 millimeters somewhere in that yellowish range. So this is 100 millimeter. And you can also look at the contact pressure. There we are, that it builds up. So good luck. We did chapter 10. Gradually, all of these chapters are going to be done. And a combination of the book and these video segments and going to class is always going to help. Good luck, folks.